Hey everyone, welcome to the lecture on section 2.5 for physical applications of integration. So we're going to do two different things. We're going to do mass and density, and then we're going to go into work. There are some other topics in this section from the textbook that you're more than welcome to read and are quite interesting, but I'm going to limit the focus for us just on the first two. So to start with, for mass and density, we're going to begin with a linear density and a linear mass. So even though the figure that you're seeing on your screen now appears to be, kind of like this three-dimensional rod, you really want to think about it as just kind of a one-dimensional, infinitely thin, like stick or needle or rope. And then the way that we're going to come up with the form to compute the linear density, the linear mass, is the same way we always do it. We're going to partition the heck out of it, and then once we have enough partitions, then that kind of becomes the integral. So if we zoom in, so first of all, we're going to let x1, because we're partitioning, we're going to let x1 equal a, and then b is going to be equal to the last slice, so xn. And so in between these things, granted this is supposed to be infinitesimally small, but we'll just have a partition here, so this will be x I minus 1 to xi. So it's just a general partition somewhere in the interval from a to b. And so every point along this line has a density, and so the density function is usually denoted by rho, which looks like a kind of fancy p. So basically, let's see, I need to add something. So in this partition, there's going to be an x value. We're going to call it xi star, and it's just some point in the partition or interval xi minus 1 to xi. So it's just some point in there. You could think of it as the halfway point, but it's more general than that. It could be closer to the left, closer to the right, whatever. So if I wanted to compute the mass for this based on density, for this little tiny sliver here, I'm going to have the density at some point in the interval, which is just rho, which is the density function evaluated at xi star, where xi star again is in the partition from xi minus 1 to xi. And then I want to multiply it by the width. So the width is just xi minus 1. So if I wanted to compute the mass, a good approximation for that would be to kind of add up all these little discrete parts. So from I equals 1 to I equals n, you just take the density function for every partition, just grab a point out of every partition and evaluate what the density is, and then go ahead and multiply it by the width. And so that will give you the sum of the masses, right? So you can think of this as like mass sub 1, mass sub 2, mass sub 3, and then adding those all together. And as we know from our previous discussions in Cal 1 on the Riemann sum and how that turns into the integral, what we can do is we can say, well, this approximation becomes an actual exact measurement when we take the limit as n goes to infinity. So what that's doing is saying, okay, so we have n partitions, and the more partitions we have, the better our approximation, the finer our estimate is. So if we let n go to infinity of this sum, then that really just becomes the integral. So that's going to be the integral from our starting point, which was x1. Well, okay, so maybe don't write that. Our starting point was x1, so we can just write it as a, right? And then our ending point was xn, so that's going to be b. And then, so instead of like designating row of xi, I'm just going to take row of x. And what this becomes, this is your change in x. This is your small width. So this becomes dx. And so for us, that brings us to, I think I left too much space. That brings us to Theorem 2.7. So if we have a thin rod oriented along the x-axis on the interval AB, and rho of x is the linear density function, then the mass is equal to the integral from A to B of rho x dx, which is exactly what we have here. So that was the whole point of this long discussion. So now we're going to go ahead and use the mass density formula in this example. So here we're given the linear density, rho of x equals to sine x, and then we're given our interval from A to B, and it's really just as simple as saying that the mass is the integral from pi halves to pi of our density function integrated with respect to x. And so sine of x dx, this is a super straightforward integration. We're just going to get negative cosine of x, evaluate it from pi halves to pi using the fundamental theorem of calculus part 2. So what we'll get is negative cosine of pi minus cosine of pi halves. So it's negative 1, positive 1. So the mass of this rod, given the density function, is just 1. So hopefully you're enjoying that these examples are a little bit more straightforward than the stuff we've been doing. I think I mentioned earlier that when it comes to applications, to a point, the integrals are a bit more straightforward than when we're just kind of practicing the theory. So next we're going to kind of step it up a little bit, add another dimension. So we want to go from linear density to radial density. And so we'll talk about where this structure for the mass comes from. So again, scooching all this stuff up. So now you have like essentially a plate, like a perfectly flat, infinitely thin plate, and the density is given radially. So like maybe the density on this circle is 1, and the density on this circle is 2, and the density on this circle is 3, and the density on this circle is 4. So you have a radial density that just depends on how far out from the center you are. And the way that we're going to compute that is we're still going to partition our disk radially like a bullseye. And so each little slice that we have in here, so like let's say the whole thing is really this, right? Like here's your whole plate. And so you're just looking at this little bullseye strip. And because the density is dependent on the radius, we know that everywhere in this strip-ish, because we have a little bit of variation of width, but more or less everywhere in this strip should have the same density. So first we want to say, okay, well, what's the area of this strip? Like, so we're partitioning our plate into radial area rings. And so in order to get the area for this, you can kind of think back to our washers. You're going to have pi times the outer radius, which is x sub I squared, minus the inner radius squared, which is xi sub 1 squared. And then the thing to notice is that this is a difference of squares. So we can express this as x sub I plus xi minus 1 times x sub I minus x sub I minus 1. So that's just an algebraic factorization of this polynomial here. As before, this distance here, this is just our small width. So we know that when we kind of are looking ahead to the integral that this will become, this is going to become our dx. And then the thing that you have to trick yourself into believing is that if you were to take this slice here, the halfway point, the midpoint between x sub I minus 1 and x sub I is x sub I minus 1 plus x sub I over 2, right? So the midpoint, like, you know, just to consider on the x-axis really quickly, if you were at the point 3 and 5 and you wanted to know the midpoint, well, it's easy for us to be like, well, duh, it's 4. But another way to do that is you can say, well, it's 3 plus 5 over 2. It's the average of those 2 points. It's the midpoint. So that's what we're doing here. So we're going to cleverly multiply this by 1. So now what we'll have is pi times 2 minus of x sub I plus xi minus 1. Okay, so I multiplied by 2, but don't worry, I'm also going to divide by 2. So I don't change the value at all. I'm just kind of like, I don't know, I feel like I'm like changing its outfit, but I'm not changing like the person that it is. So then I have x sub I minus xi minus 1. Didn't do anything there. Why do I do this? Well, the reason that I did that is because now from here I can pluck out this midpoint. So now I have 2 pi times this midpoint. I'm just going to leave a little space there for me. And then I have this x sub I minus x sub I minus 1. So this is just computing my little area that I've kind of squiggled around in the black shaded region. Okay, next mind trick, next thing you have to convince yourself of. The midpoint, x sub I minus 1 plus xi over 2, is some point in the partition from x sub I minus 1 to xi. Scrolling up really quickly, what did we call that earlier? We said x sub I star is just some point in that partition. We're going to use this same notation here as well. So instead of writing, oh, it's the exact midpoint, I'm kind of saying, I don't really care that it's the midpoint. I just care that it's some point in that partition. So instead of writing this algebraic expression, I'm just going to call it xi star because I know that it is a point in my partition. Okay, so that's area. How do we get the mass? So mass is, we can think of it as density times area in this case. So if I wanted to know the mass of this shaded black ring, it would be m sub I equals 2 pi xi star times whatever the density is for that partition, which is just going to be our density function rho evaluated at xi star. Again, xi star is some point in the partition, and I'm super not concerned where. And you might be asking, why don't you care where it is? Well, I'll tell you, because the partition is going to get so stinking small that there's not going to be a lot of options for us, essentially. So once we do the limiting function, this is going to become the integral. And so these xi stars, these are just going to become x. And then I still have my distance of my partition minus xi minus 1. So the next change I'm going to make is I'm going to call this, because it's some small width, I'm just going to call it delta x. So the final manipulation is just going to be 2 pi xi star times rho of xi star times delta x. So that gives me the mass for that shaded black ring. And so now all we have to do is just add up all the rings. Like, so I'm going to do the mass of this ring, then I'll do the mass of this ring, then I'll do the mass of this ring, etc., and so on until I've added all of them up. So the total mass is approximated by a partition, which is a Riemann sum from I equals 1 to n of 2 pi xi star rho of xi star times delta x. And then the way that I convert this to an actual perfect measurement for mass is I take the limit. So now I'm going to get m is exactly equal to the limit as n goes to infinity of my Riemann sum, which is exciting because we know this is going to become an integral. So we have 2 pi xi star rho xi star. And this becomes the integral of 2 pi x rho x dx. But what are xi and xn? So remembering that we're starting from here at 0 and working all the way out into the max, which is just going to be the radius. So this is going to go from 0 to r. And so now we have our form for, oh, there it is, I made it. Computing radial density of a two-dimensional disk or plate. So no surprise here, we're going to go ahead and do an example. So again, they give us, as in the previous example, they give us explicitly what our radial density is, and they also tell us that our radius is going to be 4. So the only thing we need to do is just kind of set it up. So we're going to get from 0 to 4, we get 2 pi, excuse me, 2 pi x times rho of x, which was the square root of x, dx. And this is another really straightforward integration. So simplifying the integrand a little bit, we're going to end up with x to the 3/2 dx. So we should get 2/5 times 2 pi times x to the 5/2 from 0 to 4. So this is just going to be 4 pi over 5 times 4 to the 5/2. So again, when dealing with rational exponents, I prefer to deal with the denominator first, just because, well, if it's easy. So like 4 to the 1/2, that's 2. 2 to the 5th, that's 32. 32 times 4, that's 128. And then I'm done, 128 pi over 5. So these examples for density are usually just little one-liners. To begin with, I'm sure I threw a hard one in the homework somewhere. All right, let's talk about work. So there is a reading question on work in the homework, so definitely read the text. But you want to think about work as the product of force and distance. That's like the first step. So, and that's when work is constant. Sorry, that's when your force is constant. So if you have a constant force, like think about pushing a rock down the street. And you're just like, you keep pushing it with the same amount of force, with the same amount of effort. Then the work it takes to push that rock down the street is just the force that you're exerting on it times the distance of how far you pushed it. We're going to kind of step that up a little bit of a notch. And we're not going to always assume that force is constant. So kind of taking that force times distance thing. So like, okay, just really quickly, like if you had force was constant, like with constant force, let's call it F. Work would equal F times distance. We know that we get distance from like your end point minus your starting point. So you have something like that. So, and this, again, this example is just in the case of constant force. So this is really the integral from A to B of F dx, where F is constant. Oh, I already wrote that. So now I want to kind of step it up a level of complexity and say force is not constant. So that kind of brings us down here to our definition, but it follows the kind of the same idea. So now, right, so our force is variable. So F is no longer constant. I guess we're just using constant force to like convince you that this is true. You could just choose to accept it though. Let's do an example with work. We're going to bring another element into the fold here that you may be familiar with if you've already taken physics. And that element is Hooke's law. So Hooke's law just talks about force and spring constants and how to determine it. So this is super important, in particular this part. So for example, 225, you're going to have, the first thing you have to do is determine your spring constant. Then once you determine your spring constant, you're going to calculate work based on the value you found for K. So writing those steps down. So we know that 10 newtons is required to compress a spring with some constant K by 0.2 meters. So for us, that means that 50 is equal to K. So done, we've computed our spring constant, and now we're going to compute work using that value for K that we just found. So we just want to go from 0 to 0.5. And remember that the force at any point X is directly proportional to the position times the spring constant. So I'm going to use f of x equals kx here to get 50x, and I'm integrating that with respect to x. So this is, again, another really straightforward integration, 25x squared evaluated from 0 to 0.5. So if you shove that in your calculator, you should get 6 1/4. And I think that is it. So this is a short little section for us. You have another section as well on centers of mass, moments, and centroids. So definitely check that one out. If you have any questions, you know where to find me. Good luck.